So we call them positional encodings or positional embeddings. So when we saw recurrent neural networks natively had the potential to calculate the relative position because we were moving in one direction, left to right, and we were moving with tightly dependent sequences. Here, our neural network or our transformer does not natively store positions, right? So we need to have a different vector, one vector for the meaning of tokens, which is token embeddings, one vector for the positions of tokens, which is positional embeddings or positional encodings. So we have to synthetically generate or store positional embedding. So let's say transformer is based on one crucial thing, which is attention. The input to attention is embeddings, right? Attention formula produces something known as contextual representation between token I and token j, right? Even that attention formula does not natively take into account or computes positional embeddings. It also relies on the input, right? So at the input end only, we need to have something known as positional input embeddings or token embeddings is always added with something known as positional embeddings. So in case of attention is all you need, the original transformer that they use something known as sinusoidal, positional embeddings. They are static. They are generated and then frozen. They are not learned. Original paper in 2007, which says attention is all you need, proposed an idea of positional embeddings, which is using sinusoidal waves. And the original transformer paper uses fixed sinusoidal functions to encode the positions of each token. Right now, embedding dimension stays similar to what we had in token dimension or token embedding dimension. Right now, what exactly is different in case of GPT? We used learned position embeddings instead of the sinusoidal version. One transformer architecture says I will use fixed sinusoidal waves. One transformer architecture says that I will use learned position embeddings. They're trying to create a parameter matrix called as WPE, which stores positions. We have seen two dimensions. One is the GPT-2 version of position embeddings, and then the other is the attention is all you need version of position embeddings. No matter whatever version we are using, we need to add both of them, right? Let's say this is called as embedding vector E, and this is called as embedding vector P. E plus P will make something known as Z, and that is going to be the output or to the attention block. This is the token embeddings, this is the positional embeddings. We add both of these vectors. This is going to act as the input to the attention block. So we have seen something known as feed-forward neural networks, right? So we have an input layer, hidden layer, and an output layer. So all the input, whenever we talk about input, mostly denoted by X, right? And whenever we talk about the predicted output, it's denoted by Y hat. It is going to produce something known as Y hat, right? And then we have something known as hidden layers, right? Everything that flows between input to the hidden layer is the weights always and always sit on the edges. A fully connected neural network is always going to have dense edges, right? From one node to every other node in the next layer. Now, when we talked about recurrent neural networks, we saw something like this. So the output y hat at time t is a function of input xt and the past hidden state or the past memory. We started with deep neural networks and we are trying to solve recurrences, we are trying to solve sequences. Now we came on to recurrent neural networks. So blue is the actual line and orange is the predicted line. So we can see that there is a very slight lag in the predicted curve versus the actual curve. The spikes are a little smoother in case of RNN's predicted behavior. The sequence length here is 3, right? I am trying to tell my recurrent neural network that find the probability of the stock price of Apple on T4 given T3, T2, T1, right? So in case of smaller sequence windows or smaller sequence length, RNNs, work nicely. But what happens when these sequence length grows, right? So tomorrow's stock price might also need global context, right? It might need past 100 days of stock data. We are treating everything in a sequential manner. How do we parallelize that computation? So we have a tight sequential dependency. When the sequence length grows, it suffers with something known as weak gradient flow. Back propagation through time, which happens in case of RNN, when the numbers are going to get multiplied, right? And let's say if the sequence length is 100, in the chain rule, when I'm going to multiply the numbers, and let's say if the values are getting smaller than 1, 0.9, 0.8, 0.08, when you multiply them cascadedly in a sequence 100 times, layer after layer, it's going to approach and tend to zero. That is what we might call as a weak gradient flow or vanishing gradient problem. The opposite is also true, that it might explode. Gradient problems, training stability is one of the issue in case of RNN, right? Forgetting things is also one of the issues in RNN. With time series talk, it behaves like this. It should ideally generate the next token and the next token, right? Since everything is sequential, there is no parallelization, right? Each word is processed after the previous one. There is very tightly coupled dependencies. We cannot process the word 10 until we have processed words 1 to 9. It's very difficult to parallelize it. So this makes the training extremely slow because GPUs cannot process multiple words simultaneously, right? Then long range dependencies are very hard to model. Like token 1 and token 100 might want to interact with each other. I will suffer with something known as exploding gradient or vanishing gradient problem, right? Gradients must back propagate through every time step in that, and over these long sequences gradients either vanish, that is they tend to go to zero, they become very small, or they explode, right? I mean, till the time you reach the earlier layers, we have already forgotten what we learned. These are all the problems we have with RNNs and LSTMs. That is why we need a better solution, which we might call attention, right? So we want to ideally design a model that obviously captures all of these sequential relationships, but what if it tries to capture without the recurrence model, without the recurrence relation, and without the convolution? We've seen convolutional neural networks, we've seen recurrent neural networks. What if we can do something different which solves all of these problems? I think we have been studying the idea of transformers, and we have seen in the previous videos what exactly becomes the input to transformers. A raw text gets converted to token IDs, right? I love mangoes. I will have a token ID. Love will have a token ID. Mangoes will have a token ID. All of them are discrete, right? Token embeddings. Let's introduce something continuous. Everything, like every token, for example 14 is a token here, that is, or 14 is a token ID that is representing I, is going to have an embedding vector, right? Embedding vector is going to be the size of D model, right? And let's say there are 1000 tokens, it's going to be 1000 into D model. Let's say D model is 64, right? It's going to be 1000 into 64. Let's say the GPT-1 model was 512 dimension model, right? Or whereas each time each embedding was 512 dimension, and let's say it had a million vocabulary, so it's going to be 1 million into 512, right? So each D model dimension is representing the size of the vector, right? And number of unique symbols, tokens, are representing the size of the vocabulary. Now one word will be represented by a D model size. So embedding vector belongs to a set of real numbers of size, vocabulary size into D model. Positional encodings, we saw the idea and narrative behind positional encodings. Some transformers, like the GPT family, want the positional encodings to be trained vectors, to be learnable vectors, whereas the other set of transformers that are specifically mentioned in the paper, attention is all you need, right? So this paper, they want to use sinusoidal waves, right? So to generate positions or to generate position vector, right? So this is the formula that they use. We don't need to get into the nuances of the formula, right? So they are trying to simulate the positions using this particular formula, but we need to understand that all of these things can be created, right? And they can be created statically, and they can also not be created and left for the algorithm to be, treat them as learnable vectors. Okay, now the input to the whole attention block is your embeddings. What embeddings? Sum of token embeddings and positional embeddings. So we will do some operations, which is element wise addition operation, to add that. You need to understand first the most basic keyword: attention. Attention is a phenomena or a mechanism where we as scientists and engineers are trying to compute contextual representation. Right now, what exactly is contextual representation? We are trying to produce some contextual representation, some sort of similarity, some sort of score between different tokens, different pair of tokens. Now, why? Because we want to understand the similarity. We want to understand the context. We want to understand, largely we want to model a language, right? Largely we want to model the whole English-like language. And English-like language is, made up of text, and then made up of words, then made up of tokens. Now, if I can understand the relationship between these tokens, right? Now, relationship is a very abstract word. Contextual representation is also an abstract word. I need to quantify a metric that explains all of whatever gibberish that I'm saying. The quantifiable metric that tells me that there is some relation between Eiffel and Tower, and they are used in the same context. That there is some relationship between king and queen, right? That there is some relationship between man and woman, right? All of these information, all of this representation will help me do the next token prediction. All of this information and representation that I do in higher dimensions of my language will help me produce quality embeddings that I might use for my machine translation. The idea that we have stuck on to is nothing but attention. There are three terms that lies in the quantification of this matrix: Q, key, and V. Q, K, and V, right? So Q means querying, K means key, and V means value. Now we can see that for between every two pairs of token, right? NC2, for every NC2 pairs, we have a score, right? We have something like a low score or a high score, right? And the score is varying. Now the score is normalized between 0 and 1. Query, key, and value. That will help us produce this matrix, the attention heat map or the attention matrix. These are the titles, descriptions, tags, and thumbnails for the millions of videos on YouTube. All the metadata that describes a video uniquely, right, is the key. Now, the actual video content, that is your MP4 file, let's say, is your value, right? So, attention mechanism is using these three paradigms: query, key, and value. Now, this is just an idea, this is just a notion, right? The attention mechanism will have numerical vectors that will represent query, numerical vectors that will represent key, numerical vectors that will represent value. So every Q of I, we are going to take a dot product or measure a similarity score with the key of J. You are going to apply a softmax function to convert that raw score into probability mass, and then you're going to pick up that score. Whoever has highest probability mass, you're going to pick that up, let's say, for example, right? So this is the idea behind query, key, and value. Now, why such a complex thing, right? Because we want to understand contextual representation, we want to model the language, right? We don't want a simple formula that is just computing a single metric. That's why we want to conquer it with a different idea of how languages are working, right? So for every token we have a query vector, right? So let's say this is the query vector for the cat sat on the mat. Similarly, we're going to have key vector, right? And similarly, we're going to have value vector, right? Now the attention formula, let us look at what the attention formula says. I will first show you the attention formula in the paper. So this is the original paper, attention is all you need. And this is the transformer architecture, the encoder decoder architecture that we might have seen a lot. Let me open the attention formula. Here goes the attention formula. Now what does it say? First, it says that attention is a function of query, key, and value, right? Forget about softmax, just only look at this. So they are saying that let's take the scaled dot product between query and key. When we take dot product, it is going to tell our algorithm that this might be the similarity between them. If the dot product has very higher magnitude, that means we have good similarity. If the dot product is very less or negative, then we have no similarity. If the dot product is 0, that means they are literally opposite or orthogonal. Query, key, and value, all of these matrices are nothing but learned weights, right? So their learned weights are represented by WQ, WK, and WV. If I multiply my input, X is my input, that is coming from the topmost layer, with the input layer. What is input? Is nothing but embeddings. What kind of embeddings? Token embeddings, positional embeddings, right? All of these matrices gets multiplied with the input to produce query, to produce key, and to produce value, right? The attention weights tells us how much to take from each token. The value vectors contain what to actually take. Attention sublayer is going to take an input as embeddings, and it is going to produce this attention matrix, right? Attention matrix is going to be an n square matrix. right? Well, let's say where n is the vocabulary size, right? So it's a very heavy computation. It's not a light computation. Deep learning has always been, has always been about deeper and hierarchical relationships, or producing deeper or understanding deeper and hierarchical meaning. One attention matrix or one head can capture nicely the syntactical relationship between the language. If I can capture multiple relationships, if I can capture the syntactical relationship in one head, semantical relationship in another head, positional proximity in another head, a relationship between subject and a noun in one head, so the relationship between noun and a verb in one head, relationship between noun and an adjective in another head, right? And if I can combine all of these heads together, right, and then multiply them with a projection matrix, or just imagine that if I can combine them together, concatenate all of these heads together and mix this information, this is my best contextual representation, right? That's why the idea of multiple heads, because we are greedy, we want to capture more and more information. Theoretically and mathematically it makes sense to have more and more heads, although it's computationally heavy, right? But more and more heads will have the capability to learn deeper and hierarchical understanding of the language. They will be able to model the language better. They will be able to understand syntactical, semantics, positional, relationship between nouns and verbs and adjectives, nouns and adjectives and everything, right? And then club them together. And the best thing is, since we are using the hardware as GPU, we can, and attention can be parallelized, right? Attention is not a sequential operation. We are keeping a global context. Multiple heads of attention can run parallelly, right? And each of them will capture different patterns, and we're going to club and mix all of this information together, right? So that's why we want to have multiple heads, right? So look at an example here. Instead of one big attention head, let's say of size 512, we're going to have 8 heads of 64 dimension each, and then at the end we can club them to get 512 back, right? So same number of parameters, but multiple heads are learning different sorts of relationships, right? So there's one more concept that I want to capture, of self attention, right? So we have seen the mechanism of attention, right, before, and we have seen how the scaled taught product attention is produced. Largely the query and key values, the query and key gets multiplied, divided by dk, the square root of dk, convert it into probability mass using softmax, and then multiply with value. All of the attention heat map or the attention formula can be parallelized, right? I am not depending, on the t-1 sequence or t-2 sequence. There is no dependency. I have to compute attention between every pair of token, right? I can parallelize that particular mathematical operation because I have the GPUs and my hardware capability to do that, right? And I can capture global context. I can capture long range connections, right? If I have a 100 cross 100 matrix, I have the relationship between token 0 and token 99, right? So because I'm storing them in a matrix, right, I will have, so with this, since I have global context and I have long range dependencies, my gradient flow will be better. I will do more and more things to make my gradient flow better, but I will show you that using this idea of attention, parallelization, long range dependencies and gradient flow, gets solved. All of these things were the repercussions or were the negative side effects of using recurrent neural networks, right? All of these were problems and challenges that we faced in RNNs. Okay.